Okay, hi. So let's say that we're making a robot, and we want to make it in a way such that it does like useful stuff. In order to do useful stuff, probably needs to like walk around and like navigate a little bit and so on. But in order to navigate, it needs to know where it is. And then the question is, okay, so how can we make it know where it is? And there's a couple of ways to answer this, and I'm going to tell you about one specific way about how to do this, and this way is called VSLAM. And the way VSLAM works is it works based purely on visual information. So let me explain what I mean by that. Wait, am I even recording? Yes, I am recording. All right. So let's say that we have our robot over here. So here's our robot. It has two eyes. It has a nice smile, like this. And it has two wheels, and it's going somewhere. It's going to the right. And then in the distance, it sees three features. So it sees a star, it sees a square, and it sees a triangle. And from the robot perspective, it looks kind of like this. So here's like a picture, the image that the robot sees at this time. So we are time maybe equal 1. And the robot sees like a small square, and then it sees like a star, and then it sees this triangle, right? So this is from robot's perspective. And then maybe at time 2, the robot has moved on a little bit, so it went a little bit more to the right. It still has its tiny little eyes and has a smile, smiling proudly, and it's going strong. Excuse me. And the features are still where they were, right? So they are like fixed fixtures. And how it looks from the robot perspective is probably something like this, that the star just got way bigger and moved a little bit to the left. The square got bigger and is still kind of central, and the triangle moved a little bit to the right and is bigger, right? So this is what the robot sees in time equals 2. And whole VSLAM, which is short for visual simultaneous, so at the same time, so simultaneous localization and mapping, VSLAM is an algorithm of figuring out, based on such information, where the robot is, and maybe constructing a map of environment such that you can localize with respect to this in the future. So we're going to build a map, a collection of those key points, like these stars and those squares and triangles. A map, we're going to build it, and we're going to localize with respect to such map. That's what VSLAM is. And there's many ways to do VSLAM, and I'm going to show one of them. And how it will work is as follows. So we'll do just 2 steps, 1 and 2, and that's going to be keyframe estimation, and then the second step is localization with respect to keyframe. So we're going to try to figure out some reference points in step 1 in the environment, and then we're going to try to see if we still see any of those key points in the keyframe, and then try to localize with respect to those try to figure out from their movement in the image, try to infer how much we as the robot have moved. And we're going to do it using two algorithms, which I'm going to summarize right now, and then over time we'll get into details of those. So in the keyframe estimation, we will use binocular. So binocular just means two eyes. Binocular depth estimation. So that's one. And then for localization with respect to keyframe, we're going to use 3D, 2D, PNP. So this is point and perspective. And all it means is optimization of pose. So this is optimization of pose such that we minimize reprojection error. Right, so let's now go a little bit into just tiny bit of details about those, about point 1 and point 2, and then over time we will get into exact details of those. So first, the keyframe estimation, binocular depth estimation. So let's say here's our robot again, just like bird's eye view, and the robot is looking to the right. It has two eyes, left eye and right eye. And of course it has the wide smile, and it's looking to the right, and then it sees our star, and then we are constructors of the robot, or maybe we just have access to the robot, so we can measure the distance between eyes, right? We just know what's the distance. Let's call it D. That's the distance between the eyes, and then the view that the left eye sees. So this is the wait, that's a bad drawing. Let me redraw this real quick. Yeah, just like a little bit bigger. So here's the left eye and here's the right eye, and what the left eye sees is tiny bit different than what the right eye sees, right? So even if I use my own eyes, when I look at the star on the screen, my right eye sees the star to the left. So that's how I'm going to draw it. And then my left eye sees the star to the right. Wait. What now? That's not what I want. Okay, that's better. Sorry. Okay, we're back. So my left eye sees the star to the right. Something like this, right? So let me draw a triangle over here, right? So starting with the eye and go to the star, and here I go to the star. So if I draw this triangle again, sort of in the bird's eye view, it looks something like this. So here's the distance between the eyes, D, and then I want to estimate how far away it is. So sort of what's the height of this triangle, and like how can I do this? So if I knew this angle over here and angle over here, right, I could use trigonometry to figure out what's the distance between those eyes. But like in fact I do know them. So if so here's sort of my wait a second, I don't like it. So here's like the optical center of the image, and here's like optical center of the image. I can sort of measure this angle. It's sort of over here, right? Like here's the alpha and here's like the beta. It's not quite it, but like we could try to figure out in just using the projective math what's the actual angle, right? We could try to work our way through the geometry of the eye or geometry of the camera and try to figure out this actually what this angle is, and then use this to measure the depth of the point that we see in the camera. And this is exactly what we do. So this is exactly the strategy that we're going to do. So we're going to repeat this strategy for many key points in an image, right? So if I see, yeah, let's maybe do like stereographic vision or something like this. Stereoscopic vision, all right. So, oh yeah, here's a good image. So, yeah, our left eye sees something slightly different than the right eye, and then if we are careful about the careful and patient about the way, basically we can write a bunch of equations and then solve for depth using those equations, and we will do this for basically many different points in the image. So we're going to pick this point and this point and this point and maybe her left eye, right eye, I don't know, all the characteristic things in the image. So this is sort of the first strategy that we're going to do, and then based on this strategy we can figure out the depth of points in the image, and this will give us keyframe. So keyframe will be sort of a pose, like a starting pose, and a collection of points associated with this pose, and each of those points we will have a depth. So maybe that I will just write it down real quick. So keyframe in our word is two things. So one is pose, like a reference. You could think of it as like it has sort of like 0, 0, 0, like a start of a coordinate frame with respect to which we can measure the future poses, right? So this is the reference. And then the second thing is a bunch of 3D points, so that are measured with respect to the starting point, and this is those are 3D, right? So they have depth is estimated. So about 2D, about two out of 3 coordinates, we're really certain for those because we know exactly which pixel each point corresponds to, right? So for example, if we take the star over here, right, we know exactly which pixel it is, right? We can just say, okay, that was pixel, I don't know, 480, 372, right? But for the depth, we have to estimate this based on like comparing from the geometry of the eyes. So yeah, and this basically concludes this keyframe estimation overview. And then in the consecutive time periods, right? So we estimated the keyframe, and then time goes on, and the robot maybe moves, and then we're going to localize with respect to this keyframe. So how are we going to do this, right? So here's our robot again. Tiny little robot with wheels, eyes, and a smile, and then it sees. So here's our keyframe, right? And then here are the points, and those points have distances estimated, right? So I have drawn those separately, right? But like really, this keyframe is sort of like inside the robot, right? This is where the robot was when it estimated the keyframe, And then with respect to keyframe, this maybe has, I don't know, a depth of 7 meters or something. This has depth of 6 meters, and then maybe this has a depth of 8 meters, right? And then basically what we're going to do is we're going to write optimization problem. So now the robot has moved, right? And then we're going to solve for x, and our x that we're going to solve for is going to be the pose of the robot. And we're going to solve, so when the robot has moved, it will see, so we will have sort of two pictures that we will want to compare. So one is like what the robot sees. The robot sees. And then number two is what we predict that the robot should see. What should robot see? So because, so let's say here's like the things, right? And then the robot was maybe like far away where it did the keyframe, but now the robot is, so yeah, I will just like do it like dotted. So the robot was here when it estimated the keyframe, but now the robot, we suspect the robot is here, right? So let's set the x to this. Just assume for a moment that the true pose is this, and then based on this we can try to predict what the robot should see, right? So okay, so the picture would be somewhat like in the front of the robot, it would be something like this, and the robot, if the robot really was here, it should see the star over here on the picture, so maybe like here, and the square over here, and then maybe the ball over here. But in reality, the robot sees this, right? So instead of seeing the bottom image, it says the top image. And then like we could draw our prediction over here as well, just like really faintly, and here as well, and here as well. And we could try to measure those distances, right? So here's like a, maybe I should use different color. Here's like the difference between those. So we predicted to see the star a little bit more to the right and to the center, but in fact we see it here, right? And then what we're going to do is we're going to say, okay, so how would I need to change the pose the tiniest bit in order to make this error that I see the smallest? So how would I change the what's the change of the pose that would make the error that I see, the visual error, the reprojection error, just tiny bit smaller? And we're going to try to so maybe it's not clear to see right now from those pictures, but we can actually write out the equations for this, and they turn out to be fairly understandable and easy to debug because everything has a nice interpretation. And this minimization of reprojection error minimization, so we're going to do this in order to figure out what's the true pose. Like whatever pose minimizes this reprojection error is going to be our true pose. So this is the general idea of the SLAM. Oh, maybe one more thing. So the system that I have described above, it's usually called front end. So front end of a VSLAM system, because so this is different from backend. So front end system is something that its goal is to quickly take in so takes in as much information as possible, right? So takes in information quickly. And then backend, and like it takes trade-off. So it wants more speed. So speed is very important, and like latency should be as low as possible. Low latency, but very important. But accuracy can be smaller. So maybe we don't really make very good depth estimations. We're not really sure where the key points are, but we should have decent tracking. So decent estimation of the progression of poses in the environment, right? So maybe the true trajectory taken by the robot was something like this, right? And then the tracking would look something like this, right? So it's like discrete, and maybe something like this. So overall it's not perfect, right? But it's like pretty decent, and like allows us to ingest all this information quickly. But once we want to have, so very characteristic thing that happens is like a drift. So because we are measuring the so when we do the measurement of the relative pose, so how much we have moved with respect to keyframe, we tend to make these small mistakes, right? So it's like, and even if we don't have bias in these mistakes, really, just over time, naturally, our system diverges, and we get higher and higher error bounds about where we think our system is. It's kind of natural property of the universe, right? It grows something like a square root of t. So our certainty where the robot really is, it will be something like this. So in the beginning we're fairly certain, right? But like as the time grows, we can become fairly far away, and like our error can accumulate, and the sum of small errors will just accumulate, and we will be fairly uncertain about where the robot truly is, and that's not a good thing. And then what allows us to control for this is the backend system. So the backend system, it's slow, or at least slower, and then it treats the whole mapping problem. So where the front end focuses mostly on the pose estimation, the backend focuses on joint estimation of history of poses, pose history, as well as the map. So positions of all key points. So backend is basically usually it's a system that takes all the keyframes and all the poses, and it remembers what the robot has seen in each of the keyframes, and it tries to figure out the relation between the keyframes, and it tries to optimize the whole thing as one system. So it says, okay, I know what's the relation of this and this pose, and this looks wrong, so I'm going to try to sort of pull it back to the same reference frame, and this and this. So it sort of tries to make those long-term links, right? So maybe it can take this and this, and it knows what's the relation of those. Well, it introduces like a type of edge between those, and then because it can use this joint information, and because it's not really constrained to be a real-time system, it can try to minimize this drift and try to consciously work against this. So yeah, this is the overview of the how it's really done. And in order to really understand it, we just need to work through a few algorithms, and all those algorithms use one language of expressing poses, and this will be the topic of the next talk. So we're going to figure out how to represent poses and how to work with them in Python. And yeah, that's it pretty much.